Now we need to prepare ourselves towards the construction of the Hart measure in the next lecture. So let me briefly talk about compactly supported functions on these topological groups, okay? So first of all, the definition. So if I have a G topological group, so you can now talk about continuous functions from G to, say, reals. Then the compact support function, the CC of G, are all those functions where f is continuous and the support is compact. So here by support, I mean you take all the x where f of x is non-zero and you take its closure. Okay, that set is going to be compact. So for these sets, we're going to deal with these functions a lot in this course. So two things that we usually do is this translation map. Okay. So suppose I have a fixed x inside G, and let's define the last translation, the Lx, to be an f from the CC of G back to itself. Basically, I do the following. So I take a function from CC of G. So here f come from CC of G, and after I translate it, when I evaluate at a point y inside G, then what I do is I return to evaluate my function f at last translation by x inverse of y. Okay, so here I do need this inverse. I'll briefly talk about y later, but here's the definition. And similarly, you do the right thing. Okay, when you right translate, you evaluate the function at f of y times x, where put the x on the right. Okay. So the reason you have a x inverse on the left but no inverse on the right is the following. So you can verify, you can basically check if I do left by x and left by y, this is the same as left by xy. Okay, so Lx by Ly is Lxy, and when you do the right, and that's also that. Okay. So sometimes you can consider this L basically maps from G to an automorphism on the CC of G. Okay, so you map your X to this LX. It's an automorphism. So on the left is a group homomorphism between G to the automorphism group. Okay, that's why you do want to put the inverse on the left so that you have this nice property. Okay. Well, the main proposition we need to prove in this video is that these left and right translation, they are kind of uniform, continuous in the following sense. So suppose I take any function in the CC of G, then if I consider the right translation by this of this f, then I take the difference with f again, and the difference, if I consider the infinite norm, okay, the sup norm, that's going to go to 0 as x goes to the identity, okay, and you do the same for the left, okay. And by the way, the CC of G is a norm of the vector space with under the sup norm, okay. It's not a Banach space, okay, because it's not complete, but it's a norm of the vector space. So I want to show that this thing converges to 0, so here's the proof. So first of all, let's fix an f that's compactly supported. So let's just let k to be the support of f. Okay, so basically it's all the x where f of x is non-zero, and you close it up. Okay, we know this is compact. Okay, so let's also fix an epsilon. Okay, epsilon greater than 0. All right. So first of all, let's do the following. So if I consider every x inside k, okay, then what happens is that I can find an open neighborhood because my f itself is continuous. There exists an open neighborhood, let's say ux, okay, open neighborhood of the identity. So that the following happens. So if I right translate by y, okay, the fxy minus f of x, that's going to be small enough, let's say epsilon over 2, if whenever my y is inside the small neighborhood. Okay, this is by f is continuous. Okay, f is continuous, so I have this this neighborhood y. And now a standard thing to do is I want to give a better estimate of this neighborhood. So let's pick some open neighborhood. Let's say Vx. That's again E is inside Vx, so that the Vx is symmetric. Okay, that's going to be useful. and then vx dot vx is again inside this ux, okay? So I pick something small, okay? So the idea is everything inside this, so here's the x, and everything, if you translate every x by this vx, then you have your function is close enough to your f of x, okay? So everything inside this x translate by vx, you have a nice approximation of your fx, okay? So that's the idea. Well, so the standard idea is that now you have k is compact, you do the open cover, you want to cover it by these nice enough neighborhoods, okay? So you cover it by these x translate by these vx, okay? So now we have, okay, so k is a union of these neighborhoods as vx, where x is inside k, that's pretty clear. So k is compact, so there exists a finite subcover. So we can now find x1 up to, say, xn inside k, so that I have this k have a finite subcover. So this is inside the finite I going from 1 to n of the xi v of xi, okay? So you have a finitely many of these nice enough cover. And now I need to pick some v, okay? So I want to show that when y is close enough to the identity, in other words, in a small enough neighborhood, then fxy and fx are really close, okay? So let's let this v to be the intersection of all these vxi, okay? I going from 1 to n. And because I have a finite subcover, so I'm taking intersection of finitely many open sets, this is open, okay? So I have something that's open. So now I want to claim the following. I want to claim that for every y inside v, if I consider the right translation by this y, and I minus the f of x, then that's always going to give me something less than epsilon. That's for all x, okay? So let's divide it into two cases. So if, first of all, if x is inside the set k, well, then what I know is that because k is, I just showed, has a finite subcover. Well, it's covered by that, but I have a finite subcover there. Okay, I don't need this one. Okay, so I know that there exists some xi where x is inside this xi. So x is close enough to one of these cover. So let's say x is inside xi v of xi for some I. Okay, so because of that, well, first of all, what we know is, recall, everything near this xi vxi, the function value is within epsilon to the xi. So automatically what I have is that the fx minus the f of xi, that's going to be less than epsilon over 2, okay? That's just because they're close, all right? So now my goal, if you look at my goal, is I want to show fxy minus fx is less than epsilon. So of course, you want to do the triangle inequality. So you have a fx here. So you just need to estimate fxy minus the f of xi, okay? So let's try to do that. Okay, so let's estimate the absolute value between f of xy minus the f of xi, okay? Well, the only thing you know is that when something is within a neighborhood of the xi, then their f value are within epsilon over 2. Okay, that's all you know. So you want to write this xy as something around the neighborhood of the xi, okay? The translated neighborhood, okay? So what you do is you want to say, well, this is f of xi multiplied by something, okay, minus f of xi, and hopefully that something is inside the neighborhood uxi, okay? So that's your goal. Well, everything is inside group, so if you want to put xi here, you need to make its inverse, and you put xy here again. And if you look at this xi inverse xy, then what do you have? Okay, so you can break it inside as xi inverse times x, multiplied by a y. And on the first component, you know x is inside the xi times v of xi, so this one is inside v of xi. And the second part of y is inside v, but v is a subset of xi, so v of xi. So this is again inside v of xi. And because we picked the v of xi, so that when you have two copies of them, when you multiply them again, it's still inside the ux, okay, this neighborhood ux. So you get something that's inside ux, okay, so this is inside ux. And whenever you translate inside ux, by the definition of ux, you get something within epsilon over 2, okay? So there we go. So because of that, you do the triangle inequality and you're done, okay? This is done. And on the other hand, so this is when x is inside k. So suppose your x is not inside k, then what happens? Well, there are two things that can happen. One thing is that if your xy itself is inside k, then what you can do is that if you look at the f of xy minus the fx, okay, what it looks like is, well, you can treat it as the following. You can put the fx first, okay, so you can think about the fxy. The xy is inside k, but the x is xy times the y inverse, okay. So here y inverse is inside v, but v is equals to v inverse. Oh, I mean, should be this way, but doesn't really matter. So is y inverse is still inside v. So xy is inside k. You do the same argument. Okay, this is going to be less than epsilon again. Okay, and on the last case, if your xy is not inside k as well, then well, you have something that's not inside k minus something not inside k, because your k is your support. The f of xy minus fx, they're just both equal to 0, clearly less than epsilon. Okay, so these are all done. Okay, so this finished the proof of this proposition. Your left and right translation are uniform, continuous.